Good afternoon. Wow, 12:31. We'll get a late start today. I apologize. There is a handout today. You don't need to get up and get it. It will still be here at the end. It is practice for the second exam. The second exam will be not this Wednesday, but the following Wednesday. I've already mentioned that I'm going to be out of town next week. Professor Alex Ishchuk will be doing both the lectures, proctoring of the exam, and discussions next week. And stay tuned for the lab instructor, so working that out. What would I say about this practice exam? Well, a couple of first of all, it's not an actual exam, meaning that I made up problems that would be very good for the exam, but I didn't time it out. I had mentioned the possibility that your exam will be broken into two parts. This is just one part, so, but what I did was I tried to make it up as if it were your exam. And what I would encourage you to do is, as you work through these problems, think about the variations on a theme, because these are the important topics, and you will see similar, though not the same, problems on your exam. For example, if you see a problem that involves calculating the pH of a solution of a weak acid, then you should also think, well, I could be asked to calculate the pH of a solution of a weak base. And if you see, similarly, if you see some sort of salt question, what is a salt, basic, acidic, or neutral, you should think of all the variations of salts that you can. I will work on a key. Ethan has offered to help and actually do it, and then me check it, and I will post it as soon as that happens. And that's before I leave or after I leave as well, because we'll be in communication. I will be in general communication with you as well. And let's see. Oh, any questions? Summer, and then.
You said a portion of our exam is in discussion, so we should Monday discussion be prepared.
Good question. So the first thing that you will have an exam on is not this Wednesday, but the following Wednesday. So if and when there's a portion of your exam that is in discussion, I'm actually thinking about it may be just on April 8th as well, part of the lecture time. So anyway, it'll be after April 3rd, which is the first portion of your exam. Oh, sorry, Dylan and then Aaron.
So like, is it going to be just the same format as like, you know, our normal exams are, or is it like what? Why is it being split in half?
Good question. Why is it being split in half? I'll start there, because I want to give you more time to do it, and I still want to ask you lots of problems. How is it going to be formatted in those two times? That I'm going to not tell you. But for example, if you see all short answers on your part that's on April 3rd, then you should probably count on there being some multiple choice questions on the discussion. Like the total exam will be essentially the same.
Oh, so it's just like a normal exam, just split in half.
It's just like a normal exam split, not probably in half, but 1/3, 2/3, with 2/3 being on April 3rd in lecture time. Aaron? Yeah. Travis?
But we should assume the total number of questions within the last exam for about 2 days?
Yeah, no, so it'll be about the same length, actually. You'll just have hopefully more time. Although, depending upon the chapter, sometimes there are more questions that are shorter, and sometimes there are fewer questions that are longer, but yes, it should be about the same amount of content. Yeah. And it should be less than this. This is too long. But this hits all the highlights I could think of. And sort of one of the ways I can make up an exam is to hit all the highlights, and then cut out 3 or 4 of them, and then I've got an exam, right? I mean, another theory on offering exams would be to ask every single question, but that would be a 4-hour exam. And we're not doing that yet. Yes, although if you've noticed, your final is 3 hours. And when I was taking general chemistry, we did have, for my class, it was an honors class, but we had 6-hour exams. And they just asked one of every question, and so you can blame my instructor for at least my desire to create that. Not that this is an honors class, but it certainly is a lot of work for a class.
I know you said you were going to record the price of AA.
Good question. Yes. So the question was about, is this what your table of values will look like? Yes. And so what I will do is I will actually start here, and then anything that I need when I make up the exam, I will add to this. And so this is sort of me starting to generate my own version of that table. And so you should use this, plus you'll have a periodic table, plus you'll have that sheet that has all the equations on it. But then, yeah, this will be it, or formatted almost exactly the same with maybe a few more values. I think the one thing that could happen is I could split it into 2 columns, if I get enough. But it should all fit on one page. All right. I don't think I have anything else to say. Otherwise, I mean, yeah, 1 page of multiple choice, a few pages of short answer questions. Okay, so where were we? We were working our way through chapter 18, that's thermodynamics. I did do some thinking and some Googling about reversible versus irreversible processes, and I'd be happy to talk about those in discussion or office hours this week. I didn't find anything necessarily that with bearing on your exam. Of course, if I did, I would tell you. Well, let's pick up where we left off then. So we had covered the previous slide about photosynthesis. We decided that photosynthesis can never be spontaneous. And now let's look at the vaporization of water. Spontaneous, question mark, at 25 degrees Celsius, question mark, at any temperature, question mark. And we're gonna, along the way of doing a pretty full thermodynamic analysis on this, we're gonna talk about what it means to be spontaneous, knowing that as we sit here with glasses of water, that some of that water is evaporating. But for now, let's do this. Let's write the reaction that we're studying here. It's gonna be H2O liquid goes to H2O gas. This is an equilibrium process, so I could put the double arrow. Typically in thermodynamics, though, you put a single arrow because typically the question is this reaction spontaneous? Okay, so we're thinking about the forward reaction. Again, I would take any set of arrows in there. But I'm going to put a single arrow there. And I'm going to then look up the delta HF values from our table. These are in kilojoules per mole. And S naught, standard entropy values. Those are in joules per mole Kelvin. And I will point out that you'll notice that every thermodynamic function in this class does have a per mole units in it. If you look online, there's a way of doing it per mole, and there's a way of doing it just delta HFs are in kilojoules. Anyway, I'm happy to talk about that. But everything in my class is kilojoules per mole, joules per mole Kelvin. Okay. I know, as you Google stuff, sometimes I forget. Well, when you look them up, you'll see that the standard enthalpy of formation for H2O liquid minus 245.8. For H2O gas, it's minus 241.8. This number is closer to positive. What we will see when we calculate this is, as you go from left to right, you do have to add energy to turn the liquid into a gas. Nothing new. We covered that in Chem 400. Entropy values, as we go here, 70.0. 188.8. And you don't have to have a particular sense for the values of these numbers. You should know that a gas of the same substance is going to have higher entropy values. We don't necessarily know how much higher. Okay. Well, there's only one coefficient here, so it's going to be products minus reactants with one coefficient. So we get delta H reaction. Delta H naught reaction is 44.0 kilojoules per mole. delta S naught reaction 118.8 joules per mole Kelvin. And you can see that sometimes, depending upon staying organized, sometimes I do kilojoules per mole and the units sort of linearly or on the same line. We can stack them up as well. First question, this process, endothermic or exothermic? This process is endothermic. Endothermic processes, do those tend to be spontaneous or tend to be non-spontaneous? Tends to be non-spontaneous, though delta G is the be-all, end-all of spontaneity. Here we are going from a lower to a higher entropy state. Does that tend to be spontaneous or non-spontaneous? That tends to be spontaneous. And I'll be careful here, I will add tends to be spontaneous. And endothermic tends to be non-spontaneous. And we have a competition between these two because one thing is tending to be not spontaneous and the other non-spontaneous. Angel, question?
So, at high temperature would be, or in terms of delta G would be negative, I think?
So, right, so Angel, your point about this at high temperature being a spontaneous process?
Both of them, since they're both.
So that's where we're going. So but that's the idea. First, I want to set up the idea that there's a competition here. And then let's start talking about delta G, because delta G is going to tell us whether this is spontaneous or not, and whether it's spontaneous at all temperatures, high temperatures, low temperatures, or no temperatures. And we're actually going to solve for the temperature at which this becomes spontaneous or not, although that, I guess, is a hint. The equation we gave last time, delta G naught reaction equals delta H naught reaction minus T delta S. And where we're going to start is we're going to start by calculating at 25 degrees Celsius, is this a spontaneous reaction? What that looks like is I'm going to plug in my delta H value, I'm going to plug in my delta S value, and I'm going to plug in 298 Kelvin for my temperature. And we're going to see what the sign of delta G is. Feel a little bit like Lord Farquaad here. That's in kilojoules. I'm going to convert it to joules. Why? Because I am a joule man. As I imagine Lord Farquaad would be, by the way. There should be a Kelvin there. Plug it all in, solve. And we get 8,600 joules per mole. And it's a positive number, so is this spontaneous at 298 Kelvin? The answer is no. No, this is not spontaneous. Non-spontaneous, under standard conditions. And we're going to say more about standard conditions in a couple minutes. Kate, question? So for entropy, this number is a higher number, which means this is matter is more dispersed. Right? Our analogy is matter is more disorganized, more spaced out though. So, and this is the hard part. So delta H, when it's negative, that tends to be spontaneous. This is positive. However, entropy, when it's positive, that tends to be spontaneous. So there are opposite signs that tend to be spontaneous. If delta S was negative, then we would write tends to be non-spon. So, non-spontaneous. For this to be under standard conditions, the pressure of our gas has to be 1 atmosphere. When water evaporates in this room, the pressure or the partial pressure of the water is not 1 atmosphere. And so, if it were, this would be a non-spontaneous process. Anyway, it is non-spontaneous according to the conditions of the air. We're not in standard conditions. Now, next thing I want to do is ask the question, at what temperature does this reaction become spontaneous? And for that, you set delta G reaction equal to 0. And I guess before we do that, I should point out that there is a temperature at which it changes from spontaneous to non-spontaneous, and this becomes an appropriate thing to do when delta at one of them tends to be spontaneous and the other does not. So the only time you're going to do this process is when either delta S or delta H tends to be spontaneous, and the other one's the opposite. Plug this in, have our values, and we're going to solve for T this time. We said last time that delta G equals 0, in this case delta G naught reaction. That's when the reaction is at equilibrium. There is only one temperature at which liquid and gas for water are at equilibrium. That's going to be the boiling point, so hopefully our answer will come out somewhere around there. When I plug this in, rearrange and solve, I get T equals 370 Kelvin. And I'm putting a little dot there because that 0 is a third sig fig. It just came out to 370. I'd rather not put it in scientific notation. 370 Kelvin, true temperature or correct temperature. Equals 100 degrees Celsius. That's the temperature at which liquid water and gaseous water vapor are in equilibrium. That's the boiling point. And this was a calculation that just allowed us to use thermodynamic values to estimate the boiling point of water. Using a lot of information we've got from this class, one of which is that delta G equals 0 is the point at which a reaction is at equilibrium. So, questions about this? Travis?
Is there any, so you're putting it at 0 for equilibrium. If we're looking for a spontaneous reaction, couldn't we use like -1 value?
Good question. So if you're looking for a spontaneous one, so at what temp does this reaction become spontaneous? Yeah, so let's say this. If temperature was larger, then this term would be a larger negative number. And so I think maybe what I should do is, since I asked the question, at what temp does this, well, at what temp does it become spontaneous? Yes. If I ask the question, looking for the inequality, at temperatures above what does it become spontaneous? The answer would be above 370 or 370 and above. Yeah. But you could put in 1 right there. You would get a temperature like 370.1. But I would say that the useful thing is to solve with the 0 in there, and then figure out, oh, it must be above for this one. Angel?
Would you do the same thing to find the temperature where it's non-spontaneous? Let's say, like it was completely off.
Yes, so at what temperature does this reaction become spontaneous? Another way I could ask the same question is, at what temperature does this reaction change from spontaneous to non-spontaneous? For non-spontaneous, you would say 370 or below 370, I guess, it would be non-spontaneous under standard conditions. Anna?
You said that if we have a difference in like the delta H reaction tends to be spontaneous, and then the delta S reaction is not spontaneous.
Right, so
like if there's a discrepancy, then
if there's a discrepancy, right, then you can do this.
okay.
If we had a reaction, and this is a very reasonable possibility on your exam, the question could say, and I forget if it's in there, I think it is actually, it'll say something like, is there a temperature at which this reaction changes from spontaneous to non-spontaneous? If so, calculate it. If not, explain why. And if there's not, then your explanation would be something like this. So let's assume this tended to be spontaneous and delta H was negative, tended to be spontaneous. Your answer would be because both favor spontaneous, at all temperatures it will be spontaneous, period, done. And if you were to do this with a positive number here and a negative number there, your temperature would come out negative. And negative Kelvin temperatures are not physically possible. So that's your hint too. Although, as we've seen, it's easy to drop minus signs as you go. However, on your exam it'll say something like, answers that make physical sense are worth a couple points. And if you tell me T equals minus 450 Kelvin, you will lose 2 of those points. But you know, or at least say, I know this is not physically possible, but this was the only answer I could get, then you won't lose those 2 points. Final thing I'd like to say about this is we talked about what standard means. We said that standard, one of the things it means is that you're at 25 degrees Celsius. Anyway, we're not at 25 degrees Celsius, but we're still going to do this calculation. And it still works pretty well. 370 versus 373 is about 1% off. Okay. So that's one of the examples, very typical example. You'll see something like that for certain on your practice exam. And good chance something like that involving that will be on the exam. We'll actually do some of those in discussion as well, some of those types of questions. All right. Now let's talk about thermodynamics and the equilibrium constant. Given the general reaction here, we can write out an equilibrium, a reaction quotient. That's what we're going to do. Reaction quotient from a few chapters ago is going to be concentrations of products raised to coefficients. And we said, well, yes, that's the same expression that we use for equilibrium constants. Except that QC, QP, Q in general was not at equilibrium. It was given any set of initial conditions. And now what I'd like to do is I'm going to create a little table here. I'm going to have some conditions over here. I'm going to have a row or a column right here for delta G reaction. And I'm going to have a column here for Q divided by K. And my first starting point here is going to be at equilibrium, and I'm going to ask you the question, what is delta G's value? And eventually you will tell me 0. That is at equilibrium for delta G. And then Q over K, at equilibrium, Q equals K. And now I'm going to have a third column called ln Q over K. What is the natural logarithm of 1? It is 0. Spontaneous forward reaction. Delta G is less than 0. Q over K is less than 1. And the natural log of Q over K is less than 0. It's less than 0, just like delta G. For a non-spontaneous forward reaction, which incidentally is also a spontaneous reverse reaction, just a reminder that the reaction is always spontaneous in some direction.
Does that mean the one before spontaneous forward will also be non-spontaneous reverse?
Spontaneous forward would be non-spontaneous reverse, yeah. Is there a question? Question, is it possible for a reaction to be non-spontaneous in both directions? It's not a philosophy class, but we'll pretend it's a philosophy class for a minute. So if the reaction is at equilibrium, it is neither spontaneous, it's spontaneous in neither direction because it's not going to go anywhere. So I think, but that's sort of like a separate third space is equilibrium. But yeah, if it's at equilibrium, no, it's not going anywhere. Is it spontaneous? Is it non-spontaneous? What is the sound of one hand clap? I'm not going to prove it, other than demonstrate it, that there is a relationship between delta G reaction and ln of Q over K. To prove it, actually, I'm not even sure I know how to do it. It would be a long derivation. But I just want to show this relationship and then present the results on the next slide. I'm going to say delta G reaction, well, it follows all the same trends as we have right here. And so I could say it's proportional to. Again, I'm not proving that. And the proportionality constant turns out to be RT. So it's going to be RT, natural logarithm of Q over K. And what I did there was I took two things that were divided by each other, or one divided by the other, and then I took them out. Question? Good question. I did take away the not, and that's on purpose. So what I said previously was that if temperature was not 298, then I would keep my not. But now, since I'm going to have any concentration, I am taking it away for sure. So if you see a delta G, without a naught in my class, it means could be any concentration, any partial pressure. Does that answer your question? So that is purposeful, although sometimes I do forget them, so keep me on my toes, please. All right. Good. What does this do for us? This allows us to now tell under any conditions whether a reaction is spontaneous or not. I said previously that water going from H2O liquid to H2O gas at room temperature was not spontaneous. If we knew the partial pressure, we'll be able to calculate that and find that it will evaporate. Well, before we do that, I'll do a quick note here. I started with QC over here. I've now gone to Q. I wanted to talk about that. If you have a reaction, so for the reaction, like this, HCl gas goes to HCl aqueous. And according to thermodynamics, the Q that you would write has anything that's in the aqueous phase as a concentration. And anything that's in the gas phase as a partial pressure. And so we have, I don't know what to call that. That's why I'm just calling it Q. Or you might call it a mixed Q because it's not a QC or a QB. Let me get a step further, and then we can talk about it. I think that's all I have to write there. So, it's like, in the special case of standard state, all concentrations are 1 molarity. For aqueous species, all partial pressures are 1 bar. Which, if you recall, is approximately equal to 1 atmosphere, and we don't really talk about the difference. And those are 4 gases. Temperature's 25 degrees. Solids and liquids are pure, but solids and liquids don't show up in Q's or K's. We'll still write it. Or at least I will. Pure solids and liquids. Now we use the example I've got right here. If my concentration at standard state is 1 molar and my partial pressure is 1 bar, what's the value of Q? 1 over 1. It's just 1. So that's why I'm going to write 1 there. And ln of Q is 0. And so when I plug back into this equation, my ln of Q goes to 0, that term drops out. And I get delta G reaction equals minus RT ln K. And before anybody asks, we're now back at standard state. And in fact, it's just said in a special case of standard state, this equation, completely general. This one, everything must be standard. So we get our constant. It comes back because everything's standard. And I'll take your question in just a second. Now, if we have a delta G naught, like on the last problem, we can figure out what the equilibrium constant is for that reaction. And perhaps more importantly for us, if we have an equilibrium constant, then we can figure out the delta G for that process as well. It ties the two together very nicely. Marissa, you had a question? And this equation is R 8.314 most definitely. And in anything thermodynamics, it is that value. I think the last time we saw the 0.08206, well, so far we have any time the ideal gas law is involved, and the ideal gas law tends to crop up every once in a while. And the relationship between Kp and Kc. Otherwise, anything with a delta G, a delta H, or a delta S, or combinations thereof, 8.31. Okay, so finally, now that for this term I have delta G, I will write one last version. Subbing in delta G naught reaction for the minus RT-LN. And if you remember, way back at the beginning of class, I said that pretty much everything is equilibrium after kinetics in this class. Now I'm showing you the relationship between thermodynamics and equilibrium constants. That's what we're talking about. We have more to do. Any questions about these? Travis?
What R value are we?
8.314. Always for thermo. Any other questions? If not, now let's start using these equations. Is the following reaction spontaneous at 25 degrees Celsius and a partial pressure of carbon dioxide equals 121 atmospheres? In my head, there was a reaction here when I wrote these notes, but since it wasn't, calcium carbonate goes to calcium oxide plus carbon dioxide gas. Very typical type of question that you might see on your second exam. Note that you're at 25 degrees Celsius. There are two ways to solve this problem. One, look up delta G formation values. Products minus reactants, etc., etc. Two, look up delta H values and S values and plug in and solve delta G equals delta H minus T delta S. You're going to be asked almost for sure to use both on your exam. This one doesn't say anything about anything other than 25 degrees Celsius, so I'm going to use delta GF values. Minus 1129.1 minus 603. 3. I think I should have put them up there, but they're there now. Minus 394.4. The hardest part of this is making sure that you don't mix up your numbers when you write them down, because these are all given to you. Delta G naught reaction is going to be products minus reactants. If you do that, you get 131.4 kilojoules per mole. Certainly, with this positive number, at standard conditions, this is a non-spontaneous process. That was not what we were asked. I guess the one thing we can use this for is we can solve for the equilibrium constant for this reaction. Let's do that next, and then we'll worry about the delta, the partial pressure part. So we're gonna find K, the equilibrium constant. I guess I'm gonna do that over here. Plug everything in. Yes. And I get an equilibrium constant 9.3 times 10 to the minus 20. Question?
Are we solving for LNK or K?
Oh.
We're just supposed to raise it to UV.
Yeah, so I 10 to the both sides. Ooh, no, I didn't. I eat both sides, right? Thank you. Now, this is a very large number, positive. That will typically mean that you have a very small equilibrium constant. Any questions about that part? If not, next I want to say, is the following reaction spontaneous using the partial pressure? I'm going to go back to this term here. Q in this case, relatively straightforward. We have products over reactants, solid and solid. So it's really just Q equals partial pressure of CO2. I'm going to put it over here. Sorry guys, I'm out of space. That's our Q equals 120. That's the given pressure. In atmospheres, could be bars as well. They're approximately equal to each other. Then I'm adding my delta G naught reaction. I'm coming up with a final value. That final value, 143. 143,300 joules per mole. Still non-spontaneous. Marissa and then Kate. good question. How do you know that Q is equal to partial pressure of CO2? Well, we know that Q is equal to whatever concentrations I give you, or partial pressures, make it into a Q. So Q sort of comes into its own almost more than it did before. So Q is going to be products over reactants. We have a solid and a solid. I guess in the previous example, it was products over reactants. There's only one non-solid product. It's a gas. It has to be a partial pressure. So technically, this is what we would formally call a QP. But what you're going to be asked to do is, if there's a gas, make it a partial pressure, and you'll know that partially because you'll be given a partial pressure. If there was an aqueous species, you would have an initial concentration. Kate? So we have two questions. Is the following reaction spontaneous? We answered that second. It is non-spontaneous. What is K? We calculated that right here. And this is so in 9 days, you are expected to be able to interpret this and come up with this. Does that answer your question, Kate?
Yeah, I just fine-tuning ways to K, but I didn't mean that point.
Yeah, no. So I guess I could have said, is the following reaction spontaneous? Reaction is non-spontaneous. To explicitly answer that, what is K? Answer. Yeah.
So I'm trying to understand the second.
This part?
No, wait.
Oh, the second.
The delta. No, sorry. Go back to the other slide. The two. Those two. Videos.
Yes.
I'm trying to understand the second one, right? Would we? I mean, plugging in Q,
Okay, so, and I will tell you this. Okay, this question, so let me refer to this question, and then we'll come back to this for a second. Not a lot here, and I'm asking a lot. However, I'm almost always asking for exactly this. So, if you see a non-standard pressure or concentration, that means you're going to have a Q, and you're going to use this version of this equation. If you're at 25 degrees, then you calculate delta G reaction based on delta GX and use this equation. The last possibility, and I think it's coming up next, is if I say, here's a concentration, your temperature is not 25, then you calculate delta H, you calculate delta S, you plug in temperature to find delta G, and we're still calling it this one, and then you plug in your Q2s.
So we couldn't have stopped the delta G reaction being positive, the one positive 130 and 124. We couldn't have stopped there since it was spontaneous because we had to factor in the partial pressures.
That's right. And so you could not have stopped here because you have to factor in the partial pressure. And like any good examiner on the exam, maybe better than lecture note writer, when you plug in the concentration of the partial pressures, it more than likely will switch from spontaneous to not to make sure that you don't. Okay. Any other questions? Yeah, so I do, there is a lot on this. I realize it's the last thing we do before the exam too. And you will find, and this used to happen in Chem 400 too sometimes, that there's a little less depth on this, just being honest. So know the problems on the practice test, know the problems on the homework, and that's pretty much the material covered. Esperanza? How did I get this? Good question. I took products, which would be, and minus reactants, and I got that. Well, yeah, that works. Oop, I had another page to do all those calculations. Now let's do these. I think I threw off my system. There. Calculate the solubility of lead chloride lead 2 chloride, as a function of temperature at 25 and 50 degrees using only thermodynamic data. Actually, this is not exactly the kind of question from before, but it's related. And I will point out to myself, I have 2 pages to do this. And like anything in Chem 401, having to do with equilibrium, thermodynamics, or anything else, so we're going to start with a reaction. That reaction is going to be a KSP reaction. And we know that because it's solubility of lead 2 chloride. And the next thing you're going to do is using only thermodynamic data, you're going to note that while you are at 25 degrees, you're also at another temperature. At any temperature other than 25 degrees Celsius, you need delta H and delta S. So a temperature does not equal 25. You got to use this term to figure out what delta G will be at non-25 degrees. Travis?
So your delta G has been off there, but it's not at a 25 degree standard because you're using the standard choosing output.
Yes.
Okay.
And that's, no, that is counterintuitive, let's say. So, yes. And sort of how I figured out to do it, remember I think I said I played with having an asterisk here because we're not at 25. And I said, well, since these 2 are still standard, even though it's not 25, I just stuck with the non-standard. You're right, I'm open to new possibilities that would be more clear. Because I've tried. Yes, to answer your question, that's true. Marissa? Good question. Why can I use this when temperature is not standard, but then down here I lose my when my partial pressures and my concentrations are not standard? Good question. I don't know. So would you feel better if I went like that? And then I said T, not standard. But other things are standard? I don't know. That's a good question. Why does it still give me a reasonable answer? All right, you asked for it. No, it's not that bad. So why does it still give me a reasonable answer? So for example, when we did this for water, standard conditions is 25 degrees, but water boils at 100, and it was still pretty close, 1% off, we've decided. That's because delta H, oh, I'm so glad I have 2 pages now. All right, so I'm erasing this crap because I'm not doing it. It's too late. If you think I should do it next semester, write it on a tiny piece of paper And then I will play the world's smallest violin. No. Seriously though, if you have a better, more systematic way that you understand it, please do. Let's talk. I am always looking for them. Why does calculating delta G naught not at 25 degrees work? Here's the answer. Well, let's talk for a minute about what delta H means. Because delta G is made up of delta H and T delta S. What does delta H mean? Do you remember back in Chem 400, we made reaction energy diagrams? And we said that the difference between, let's say it's an exothermic reaction between reactants and products was delta H, right? Do you remember what we put on the y-axis? Potential energy. And that's because we talked about it, though we didn't say too much more, we talked about it, that delta H relates to the potential energy change from reactants to products. Because as you break bonds and make new ones, and we actually had that whole bonds association energy thing where we calculated for average bonds and we got good values for delta H. Again, plus or minus 5 or 10% is pretty good. Delta H, and whether it's got the naught or not, but let's do the one that we're talking about now. Delta H relates to potential energy change from reactants to products. And the potential energy is stored in bonds. And if you are a bond at 25 degrees Celsius, and you're the same bond at 100 degrees Celsius, you're pretty much in the same positions. And therefore, you pretty much have the same potential energy. Unless you break the bond, but the bond's not breaking. So, relates to potential energy change from reactants to products. Potential energy is stored in bonds. Bonds don't change much as temperature changes. Bonds don't change much with respect to temperature, WRT. That's what, and then it says under with respect to. Do they change? Yes. You can imagine that if at a higher temperature there are more vibrations, that's what they do change a little bit, but largely they don't. Matter dispersal, delta S. Similarly, although more abstractly, if you've got the same number of particles and the same dispersed in roughly the same number of states, the number of states doesn't really change as temperature changes. And so delta S doesn't change much with temperature either. Does it change? A little bit. And typically, when delta H changes, delta S changes in the same direction, which would mean that they cancel each other out. Delta S naught reaction relates to matter dispersal, which doesn't change much with respect to temperature. Fabulous question, Marissa. Thank you for asking it. Why does this work? because these two terms don't change very much, and what changes is this temperature. And so it's like two near constants. The big effect on G is the change in temperature. So that's why it works. Question, when you change concentration and pressure, does that change the bonds? No, that changes, think of that as more of changing it in a Le Chatelier's principle sort of way. You're creating more molecules on one side or putting more molecules, which drives the reaction to go in the other direction. So it's different. Which is not a complete answer, but can you see that it's at least different? Yeah, it's a different mechanism. Any questions about that? All right, so it does work. It works pretty well, not perfectly. It's sort of like bond energies. Okay, so I guess to finish answering this question, why does blah, 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 not? That's the worst English sentence I think I've ever written, isn't it? Why does calculating delta G naught reaction not at 25 degrees work? I got, that's one thing there, so, okay. Why, a better way of saying it word in English class would be, why does calculating delta G at temperatures other than 25 degrees work? All right, so good. I had all this space. I've used up half of it already. Let me write this reaction again on the other page. And then I could look up all the values for delta HF and S naught and delta GF and then write them all out. I'm just going to write the delta blank reaction values. Delta H naught reaction, 26.1 kilojoules per mole. Delta S naught reaction, minus 5.5 joules per mole Kelvin. Delta G naught reaction, 27.3 kilojoules per mole. Before we go, is there any temperature at which this reaction will be spontaneous? Well, let's see, delta H, does that tend to be spontaneous or not? Tends to be not spontaneous. Delta S tends to be spontaneous or not? Non-spontaneous as well. There is no temperature at which this reaction will be spontaneous at standard conditions. Not possible to be spontaneous at standard conditions. I'm going to write out, so I'm working my English. There is no temperature at which this reaction will be spontaneous at standard conditions. Now, we have delta G reaction that's under standard conditions. That's at 25 degrees. If I want to find K for this, it will be a KSP because I've written out a KSP reaction. That's the only way we know that. That's the general form of the reaction. I know it's a KSP. only because I wrote a KSP reaction. The K in this equation corresponds to whatever it is up here. If I give you a random reaction, just call it K. We would call it KC if it was chapter 15. If I write a Ka or a Kb reaction here and I have you calculate delta G, then write Ka or Kb there. That might be helpful too. I know my delta G. I can solve for my equilibrium constant. So I know my value here. I've plugged in twice already for R and T. R is the 8.314. It says right here 25 degrees Celsius, so my T will be 298. Sorry, I shuddered because I did not write units after numbers there, but I'm going to keep going anyway. Mathematically rearrange, you get KSP equals 1.8 times 10 to the minus fifth. I will let you do that math. Now, if I want to solve for the solubility, that was the question we were asking, calculate the solubility. I would have x times 2x squared and that subs for an ice table that I didn't do. That ice table was for the last chapter, but I'm skipping that part for now. At 50 degrees C, question loaded?
That seems like a fairly significant polarity here. And so I'm wondering how that works when you're saying this is not a spontaneous reaction. Because it's not spontaneous for the lead chloride to dissolve. Why is it not dissolve?
Good question. The question was, this is a non-spontaneous reaction. Why does so much of it dissolve? If this number is less than 1 molarity, which is standard state conditions, this number will be positive and tell you it's non-spontaneous. That's right. So that's why we are forced to think a little bit about standard conditions right now. In the same way, really, when we were thinking about what's the difference between water evaporating and water boiling. Water boils at 1 atmosphere, and so it can still happen, but not be considered spontaneous. And yeah, does that answer your question? Yeah, that's a tricky one. Think about it. Yes, Aaron.
What were we trying to find?
What were we trying to find at 25 degrees?
Yeah.
So we'll come back to the question. It says calculate the solubility of lead 2 chloride as a function of temperature at 25 degrees and 50 degrees Celsius using only thermodynamic data. So we calculated delta G naught reaction. We used an equation to solve for KSP. And then that KSP we used to find the solubility. This is subbing in for an ice table from the last chapter. I'm going to keep going, but I do want to make sure you understand this, so we can talk about this afternoon if you want us to, and make sure that this makes sense, because today is solubility day in discussion too. So anyway, let's talk, but this is subbing for an ice table. Next thing I want to do is do it at 50 degrees. At 50 degrees, I have to use delta H minus T delta S. My T at 50 degrees is going to be 323 Kelvin. And I get this time with a negative and a negative, that's going to mean this term becomes positive. My number should be bigger than this, and indeed, 27,900. I seem to be out of space. Nothing up my sleeve. There's another page. Let's do the rest of the calculation on the next page so we have a little more space. And how about this? I see wide open spaces here. Why don't we do the ice table this time? Except not in that. We can now find our KSP at 50 degrees Celsius. We plug into the same equation. I think my pens are going to make it. 6 more minutes. Now we're at 323 Kelvin, so we have to plug that in. Ln. Okay, and this is equals. Bring these two over to the other side, solve for KSP. You should get 3.1 times 10 to the minus 5th. Now let's do the solubility ice table. It's going to be the same reaction for KSP. Like all ice tables where we have a K value, this is going to be in terms of molarities, well, as far as aqueous species. As far as our solid, it doesn't have an initial concentration, but some of it does dissolve. and solving for solubility, we get 2.0 times 10 to the minus 2. Does the solubility change? Well, in a minor way. And if you look way back in your notes at the beginning of the solubility chapter, we looked at lead chloride dissolving as a function of temperature. We showed you a little movie. Yes, as temperature increased, more of it dissolved. Just enough dissolved to make this problem work. Makes me look like I was planning. Who knows if I actually was. Any questions about this? Lovely. Wow. This does not look like the kind of thing we can start talking about in 3 minutes, so we will end a couple minutes early today. We will finish up just these last few pages of chapter 18 and then on Wednesday. Then we will start chapter 19, which will not be on your second exam. Never a dull moment.